Today we start our next unit, which is called dynamics. We're not going to go very far with that today, but we will begin it. Talk about the similarities between kinematics and dynamics, what the differences are between kinematics and dynamics, and then we'll go a little bit further with the whole idea of dynamics. If you remember from Unit 1, kinematics, the one you just finished, is the study of motion without regard to what causes the motion. So in other words, we're talking about the car traveling down the road. We don't care what got the car moving. Okay? We're talking about the boat going across the river. We don't care what got the boat moving. We care only about the motion itself, not what causes the motion. Dynamics, on the other hand, dynamics is a study of motion with regard to what causes the motion. In other words, dynamics is the study of what causes motion. Okay. Energy. We will talk about energy in this unit, but more fundamentally, force. It's a study of forces. So we're still going to look at motion here a lot. The equations that you learned in this unit, especially the group B equations, we're going to use quite often. But we're introducing now not only the motion itself, but what caused that motion in the first place. In other words, the forces that caused that motion. Let's define a force. This is not new. You guys have defined a force back in grade 6, maybe. A force is defined as a push or a pull. That's it. Whatever definition that you got way back in grade 6, the push or the pull, is exactly the same definition that we use in Physics 20 and the one that we will use in Physics 30 when you take Physics 30 next year. Now, I suspect when you learned about forces in grade 5 or grade 6, you didn't learn about what a force can do. There are two things that a force can do to an object. Number one, it can accelerate the object. Now, when it accelerates the object, that can include all kinds of different things. It can cause the object to speed up. That's accelerating. It can cause the object to slow down. That's accelerating. Decelerating, but that's still a form of acceleration. It can cause the object to start or stop, which is kind of like speeding up and slowing down, I suppose. But it can also cause the object to change direction. Even if an object goes at a constant speed around a turn, it's still accelerating. Think about that for a second. Doesn't seem to make sense on the surface. A car is going around a turn at 100 kilometers per hour, not speeding up, not slowing down. How can it possibly be accelerating as it goes around the turn at a constant speed? Well, how do we define acceleration? The rate of change of, acceleration is the rate of change of what? Velocity. Good. Velocity is a what? A vector or a scalar? Yep. Vector. Good. So if it's the rate of change of velocity, and velocity is a vector, and you're not changing speed, you're not speeding up or slowing down, but you are changing direction, and velocity is a vector, then you must be changing your velocity. If you're changing your velocity, you're accelerating. So an object that goes around a turn or changes direction is experiencing an acceleration, even if it's not speeding up or slowing down. When it goes around a circular turn, we call it a centripetal acceleration. We'll talk a lot more about that in our next unit on circular motion and gravitation. So the first thing that a force can do is cause acceleration in one of these ways: speeding up, slowing down, starting, stopping, changing direction. What else could a force possibly do besides cause acceleration? Speed up, slow down, change direction, so on. Well, a force can also deform something. Watch me right now. I'm pushing on the wall. I'm pushing pretty hard on the wall. Am I accelerating the wall? Am I causing the wall to speed up? No. Am I causing it to slow down or change direction? No. What am I doing to the wall? Well, I'm not doing very much to the wall at all. But if you were to look at it from the end, you might see a small deformation of the wall. Instead of the wall being straight up or straight down like this, maybe the wall is slightly bowed in now like this. If I cause the wall to deform, then I must have applied a force. Now, it's possible to do both. When a car is involved in a crash, does the car deform? Yeah, it does. It deforms because of a force that was applied on the car. But does it also accelerate? Yeah, it probably either speeds up or slows down or changes direction. So it's possible to have both, but it's not necessary to have both. Okay, a force can do one or both of the following things. It can accelerate the object, or it can deform, or change the shape of an object. Now another term, the net force. The net force. What does net mean? Not in the context of like fishing or something, right? Catching something, but in terms of mathematics, in terms of financial, even. I'm thinking of right now financial transactions, yeah. Overall or total, yeah, right. I get paid on the 25th of every month. There's two columns on my pay stub. The first column is for the gross. And the second column is for the net. My gross salary has one number on it. Okay? It's just a simple number. I get a certain amount of money per month. That's my gross salary. My net salary includes a whole bunch of numbers. Maybe I get extra pay because of something. Maybe I get money taken away because of Canada Pension or employment insurance or my pension plan or income tax. At the bottom of that column is my net salary. My gross is what I started with. My net is the total after I add everything into it or subtract things from it, right? So my net would be an overall, as Lewis said, or a total, as Lewis said. That makes sense? I don't know about you, but I think it should be the other way around. Okay, when I look at my pay stub, this is not the number that's gross. This is the number after they've taken off income tax and employment insurance and pension and all the rest of the stuff. This is the gross number. This is the number that ends up being not much more than half of this number. But anyways, we call that the net salary. Well, the net force would be the total force. What term did you use? The overall force. The unbalanced, sometimes we call it, the unbalanced force. When we add all the forces together, both positive and negative, the net force would be that total overall unbalanced force. I want to say it's the total or unbalanced force. Now listen very carefully. I'm going to give you a couple more definitions here. But remember this right now as we go through these definitions. It is a net force that causes motion. It is a net force that causes motion. Right now, Leah's desk has multiple forces acting on it. I'm pushing on it one way. I'm pushing on it the other way. There's friction acting on it. There's gravity acting on it. There's another force of the ground pushing up on it. There's all kinds of forces acting on it. So why isn't it moving? Because they're all balanced. The overall force is zero. The net force, if there was a net force, an unbalanced force, a total force, that's when our desk starts moving. So unbalanced forces or net forces start causing motion. All right, a couple more terms, and then that stuff will make a little bit more sense to you. Inertia. You've heard that word before, right? Grade 7, you probably watched a Bill Nye video. And what do they say at the beginning of the Bill Nye video? Inertia is a property of matter. Right, remember that? Inertia is a property of matter. It is the tendency of an object to maintain its current state of motion. In other words, if an object is moving, it wants to keep moving. If an object is at rest, it wants to stay at rest. It doesn't want to change what it's doing. It's kind of lazy. Okay? Objects are kind of lazy that way. They're doing something. Okay, it took some energy or some force to get them doing it. They want to keep doing what they're doing. If you're sitting on the couch watching a football game, you don't want to get off the couch. You want to stay there, right? You have inertia. If you're moving, you don't want to bother trying to stop. Okay, it takes too much energy to try to stop. You want to keep doing what you're doing. You have inertia. The tendency of an object to keep doing what it's doing or to maintain its current state of motion. It depends on one quantity. It depends on one thing only. It depends on mass. How likely an object is to keep doing what it's doing depends upon how heavy that object is. Okay, Leah's desk again as an example. Okay, Leah's desk has quite a bit of inertia. It really wants to keep doing what it's doing. It really wants to stay at rest. Leah's water bottle, on the other hand, has inertia. It wants to keep doing what it's doing as well. It wants to stay at rest. But it doesn't have nearly as much inertia as the desk. Right? When I push the desk, it's hard to get it moving. When I push the water bottle, it's not hard to get it moving. Why? Why does the desk have more inertia? Because the desk is heavier. Right. Okay, a car is traveling down the road at 100 kilometers per hour. It's hard to stop that car, right? A train is traveling down the tracks at 100 kilometers per hour. Which one's harder to stop? The train. How come? Heavier. It's got the same speed, but it's heavier because it has more inertia. The train wants to keep doing what it's doing even more than the car wants to keep doing what it's doing because it's heavy. Static equilibrium and translational equilibrium. Almost done with the terms here. The word static means not moving, stopped, at rest. Static electricity, as you learn in Physics 30, is electricity that's not moving. If you do engineering in university, one of your first courses might be a course in statics. That means analyzing objects that aren't moving. Static equilibrium means balance, because that's what equilibrium is, right? Learn about equilibrium a little bit in biology class. Balance. Balanced forces when an object isn't moving. So we'll say balanced forces acting on an object at rest. Leah's desk right now is in static equilibrium because all of the forces that are acting on it, and there are lots of them, they're all balanced. If there's a force to the right, there's a force to the left that balances it. If there's a force up, then there's a force down that balances it. They all add up to cancel. They all add up to give me a zero net force. It's in static equilibrium. It's at rest, and the forces are all balanced acting on it. So the object at static equilibrium wants to stay at rest. If it's at rest, it wants to stay there. Translational equilibrium means we have balanced forces acting on an object that's moving. If the forces are unbalanced, then the object that's moving will accelerate. But if the forces are balanced, in other words, it's in translational equilibrium, then this object that's moving will keep moving. It will. but specifically, it'll keep moving at a constant speed or a constant velocity. Remember, what do you need to cause something to speed up or slow down? To cause something to accelerate, you need a net force, an unbalanced force. If you have balanced forces, there's no reason for it to speed up or slow down. The object will never stop. The object will never go faster. It will keep going forever and ever and ever at that same speed if the forces are balanced, if it's in translational equilibrium. A spacecraft hurtling through space at a constant speed is in translational equilibrium. It's moving, it's not going to stop, it's not going to speed up because the forces acting on it are all balanced. It will keep going at the same speed forever. Leah's desk, now it's going to stay sitting there forever unless somebody causes an unbalanced force and takes it out of static equilibrium. Equilibrium means no net force. It's either moving, translational, or static, not moving. We're almost done. This is the last thing. Newton's first law, also called the law of inertia sometimes. This kind of ties it all together, everything that we've done here so far today. You guys have heard this before, I know you have. Newton's first law has two aspects to it. The first aspect refers to an object that's at rest. An object at rest wants to stay at rest. In other words, an object in static equilibrium will never move unless something happens to it. Until an unbalanced force acts on it. If it's in static equilibrium, the forces are all balanced, it's just going to stay there forever and ever and ever until somebody pushes on it to cause an unbalanced force, to cause a net force. The second aspect is an object in motion. What happens to an object in motion? What's the tendency of an object in motion? What does it want to do? Wants to stay in motion. An object in motion stays in motion, but specifically, it stays in motion at a constant velocity. Which includes a straight line, right? If it's a constant velocity, it can't be changing direction. So an object in motion stays in motion at a constant velocity in a straight line until acted upon by an unbalanced force. In other words, until a net force acts on it. Not just a force. You're driving down the road at 100 kilometers per hour. Your car is traveling at a constant speed. There is a force acting on it. There's air resistance. There's also friction. There's also the force of your tires on the road. There's lots of forces. It's going to keep going in a straight line at constant velocity, though, until there's an unbalanced force, until something acts on it that can't be canceled with some other force. We'll give you a couple examples of Newton's first law here, where we can put this into action here. Years ago, I remember I was, this is probably 15 years ago now. I was sitting in my fairly new car. I'd only had it for a few months. I was sitting at a stoplight in Calgary. At the time, it was the first stoplight as you drive into Calgary. It's where Shaughnessy is, right? And now there's a couple stoplights before that. But I remember seeing the red light, so I slow down. I stop at the red light. The lady behind me also sees the red light. She slows down and she stops. The difference is I waited for the green light to start She didn't for whatever reason. She just put her foot on the gas pedal and started going before the light turned green, and she ran into the back of me. Thankfully, she wasn't moving very fast when she hit me because she had been stopped. She stopped for the red light. Then for whatever reason, maybe she saw green flash in the corner of her eye, whatever, she started going. So she hit me from behind. Okay? It didn't hurt my neck. I didn't get whiplash, but I didn't get whiplash only because she wasn't moving very fast when she hit me. When she hit me, here's what happened. My body was at rest. My body inside the car was going to stay at rest forever unless an unbalanced force acted on it. Well, when that lady behind me hit me, that lady applied an unbalanced force on my car, on my seat, on my body. What happened to my body? My body went forward. What happened to my head? What happened to my head? Okay. Yeah. Yeah, I did have a headrest, yeah. So, I mean, that's a big thing. We'll talk about that in just a second here, but why it's important to have a headrest in your car. It's just as important as a seat belt, really. It is. And to have it adjusted properly, just as important as a seat belt. My head didn't go back, and your head didn't go back either. As much as you think your head went back, it didn't. Your head was at rest. What happens to it when you're hit from behind? Your head stays at rest, but your body goes forward. So it seems like your head flings back, but really your head just stays where it was. But as your head stays where it was and your body goes forward, it gives you the illusion that your head is going backwards, right? Nevertheless, it bends your neck and gives you whiplash if you're hit hard from behind, right? So an object at rest, that was my head, stays at rest until acted upon by an unbalanced force, okay, which ultimately was my neck, okay, but thankfully wasn't a very hard force, so it didn't really hurt my neck dramatically. Another example, when I was your age, I drove well, when I was a little bit older than you guys, I think I started in grade 11 actually. I drove a delivery truck, a dry cleaning delivery truck. It was my Saturday job every week, and in the summertime I did it 5 days and sometimes 6 days a week. Yeah, I remember one Friday afternoon, sometimes I'd have to do it on a Friday afternoon during the school year as well. One Friday afternoon, I remember there was some snow on the ground, just fresh snow, and I was just a fairly new driver. I was coming off of the highway, okay, kind of like the QE2 highway, on the off-ramp to come down into this town. So here's the highway, okay, the double highway. Here's a northbound lane, here's a southbound lane, and then here's an interchange that I got to come down and then go under the highway right here into this town. As I come down this, come off this highway at almost 100 kilometers per hour, because the road was pretty good up here, I hit some ice right here. What happened to me? I wasn't going 100 kilometers per hour at this point. Thankfully, I'd slow down before I got to this point. But I was still going fast enough. I hit some ice, and I went off in a straight line. Here's the guardrail, and I hit the guardrail. So my boss loved that. I just started working there like a few months before, and all of a sudden I just hit the guardrail with the delivery van. What happened? Yeah, right. All of a sudden, the forces were balanced. I had an unbalanced force. Friction provided me with an unbalanced force as I was going around this turn. But all of a sudden, as I hit a patch of ice, the forces balanced. There was no friction anymore. When the force is balanced, what happens? An object in motion wants to, in a straight line at a constant velocity, right? So I went in a straight line at a constant velocity. I didn't slow down. I didn't change direction until there was another unbalanced force acting on me, which was the guardrail, right?